Good morning. I want to welcome you to the fourth annual Discovery Farms Multi-State Webinar. We really appreciate you choosing to spend time with us today, and we will cover several water quality topics and the role of on-farm research in informing these topics. Over the course of the morning, we'll be featuring the work of Discovery Farms programs in Wisconsin, Minnesota, Arkansas, and Vermont. My name is Amber Raditz. I will be the moderator for the day. I'm the Agriculture Water Quality Program Manager at the UW-Madison Division of Extension, which is the Wisconsin home of the Discovery Farms program. This multi-state effort is in place to provide farmers, farm advisors, and interested stakeholders with credible water quality research information. A few housekeeping things before we get started. First, we really encourage questions and discussions from you. So please put content-related questions in the Q&A box, which can be found at the bottom of your screen. Please put questions related to logistics if you're having issues with technology, have questions about the agenda, or other logistics into the chat box. And those messages will go straight to the hosts and panelists, and we'll address those separately from the Q&A that is for our speakers. Secondly, if you'd like to receive CCA credits for your time here today, we will show the QR code at the end of the session. At that time, you can scan the code from your phone to register for credits or put your CCA number in the chat and we can register them for you. There are 1.5 soil and water credits and a half credit of nutrient management available for today's webinar. The plan for today is that each state will have 30 minutes of presentation time, including answering questions. Each speaker will answer questions at the end of their talk. There might be some time at the end of the session for questions, but we encourage you to ask questions right away during the speaker time and also use the Q&A feature to vote for questions that resonate with you. As a little bit of background, Discovery Farms was first established in Wisconsin in 2000. It was formed in response to a call from the agriculture and environmental communities for enhanced on-farm research in the area of water quality. Farmers volunteered to host water quality monitoring stations in Wisconsin to better understand the dynamics of runoff timing, the impact of ag management, and the influence of weather. Over the years, programs have been added in Arkansas, Minnesota, and Vermont. Representatives from each state pursued the determination of Discovery Farms, which is a registered trademark, because of the positive response to the work of the program from farmers, farm advisors, agency partners, and water quality stakeholders. Each Discovery Farms program has to include the 3 pillars of Discovery Farms, including farmer leadership, credible water quality research, and communication of results. Okay, let's get started with our speakers. Our first speakers of the day are Lindsay Hartfield and Ellen Albright. Lindsay joined the Discovery Farms program within UW-Madison's Division of Extension in January 2023 as their research program manager. Prior to joining Discovery Farms, she completed her PhD in Agriculture and Biosystems Engineering from Iowa State University, where her research was focused on water quality, engineering conservation practices, and tile drainage. Ellen started with Discovery Farms as a researcher in December 2023. In this role, she assists with maintaining on-farm field sites, data analysis and visualization, and building research partnerships. Ellen received her Bachelor of Arts in Biology from Macalester College and her PhD in Freshwater and Marine Sciences from UW-Madison. Go ahead, Lindsay and Ellen.
Thanks, Amber. I will get my screen shared. Okay. If you can see that okay, I will go ahead and kick us off this morning. Thanks, Amber, again for that great introduction. Today, I will be kicking us off with Wisconsin Discovery Farms data, highlighting how we're using this data to evaluate agricultural conservation practices. Before getting into that data, I did want to provide just a quick overview for everyone on kind of the state of the Wisconsin Discovery Farms program, where we are currently monitoring, what kind of projects we have, and where we're headed in the near future. I will start by highlighting our nitrate leaching sites, and these sites are monitoring infield drainage and nitrate leaching below the crop rooting zone. The reason we added this type of monitoring a few years ago is in response to the state having a growing concern for elevated nitrate concentrations in our groundwater. So we added this type of monitoring a few years ago, first in western Wisconsin in Pepin County. And this site is looking at manure management on sandy soils, and it's designed and installed with a before-after control treatment study design that is going to allow us to test different conservation practices or management strategies to see how effective they are at reducing that nitrate leaching. The next site I'll highlight here is in southern Wisconsin, and this is in Rock County, Wisconsin, looking at nitrogen management in a cash grain rotation. And the last of these sites that we have installed is in eastern Wisconsin on a dairy forage rotation. Treatment still to be determined on this site. This one was installed a year ago, so we're wrapping up our first year of monitoring on that site currently, still figuring out the treatment on that one. But we are looking to be adding some new sites this year in the central Sansa, Wisconsin. For those who are not familiar with that area of the state, there is a lot of potato production, a lot of vegetable production. So in those monitoring sites, we'll be looking at how to reduce nitrate leaching in potato production areas and rotations. Next up, I will highlight our surface runoff and tile drainage monitoring at the edge of field. Our surface sites, our primary focus is looking at soil erosion and phosphorus losses. So I'll highlight those first. We have 3 monitoring sites in Langlade County, Wisconsin, where there's a lot of seed potato production happening. This is an area of the state where we previously hadn't had any monitoring. It's also a farming system we hadn't previously monitored. So we're really just trying to understand soil and nutrient losses for that type of production system. Next up, we have a few sites in Marathon County, where we're looking at the effects of continuous cover in row crop versus grazing systems. And last up, in eastern Wisconsin, we have 2 surface monitoring sites on dairy forage rotations, and you'll get to see a little bit more of that data in the coming slides. But we also have 1 site where we're monitoring for tile drainage, specifically with a wood chip bioreactor to treat that tile drainage and hopefully reduce the nitrate leaving the tile drainage system. So that's a practice that's growing in popularity in our neighboring states. Haven't really investigated it much here in Wisconsin, so we're really excited to have this practice to see how effective it is in our cold northern climate. So that's kind of where we are currently for the program. And historically, we've really done a lot of this monitoring to understand the timing and magnitude of losses in Wisconsin across the varying landscapes and farming systems that the state has. But moving forward, we are going to shift our focus a little bit and have some more structured research questions and study designs. We needed this really strong foundation of what kind of losses we were having, what the magnitude of those losses were, when they were happening. And now that we have that base foundation, we can get a little bit more targeted with the research questions we're looking at. And the goal behind this is to better understand both the mechanisms of soil and nutrient losses, but then also to evaluate specific conservation practices and see how effective those practices are on our landscape. And the reason behind this is that we really want to be able to provide science and data supported recommendations to our farmers across the state. And with the varying landscapes in Wisconsin, we want to be able to provide local solutions to their water quality problems. So that's where our program is and where we're headed in the near future. And now I'll transition and focus in on a case study of evaluating practices to control soil erosion in a dairy forage rotation. So I'm going to kick things off right away with some data here, and then I'll give a little bit more site background. But here I'm showing us one of our monitoring sites. You're seeing total annual soil loss on the y-axis, so our vertical axis. And I want to draw your attention that there is a break in that graph. So it goes from about 3,000 pounds per acre of soil loss to up to 10,000 at that break. And you're seeing, soil loss across 5 years of data. Now I want to pose a question to you. I know we're on a virtual format, so I don't expect you to actually answer this question, but I want you to think about this. Think, when do you think they were using no-till and cover crops at this site? So I'll give you a second to think about that. Okay, so I'm thinking you're probably thinking something, maybe around 2021, they did something different there. And you'd be right that something different happened, but you might be surprised to hear that this was actually a trick question and they were using no-till and cover crops the entire monitoring period. So all 5 years they had no-till and cover crops in place. But as you can see in 2020, they still had really tremendous levels of soil loss, upwards of 50,000 pounds per acre of soil loss. And then if we look at 2021, they were actually under 500 pounds per acre. So just a really huge reduction in soil loss in that time period. So now you're probably asking, well, what did they do? What did they change? In 2020, they added a grassed waterway in place. And so this is a really great case study to show the importance of protecting those concentrated flow pathways as a first step in our conservation journey, prioritizing protection of concentrated flow pathways. So we'll continue this message here as we go across, but I'm going to give you a little bit more background on this site now. So this is one of our monitoring sites in Kewaunee County, Wisconsin, in northeast Wisconsin. A little bit more background on this monitoring site. It's a about 2.6 acre basin that we're monitoring. Has moderate slope, 4%, silt loam soil, and again using the no-till and cover crops. And then in terms of cropping, most of the time it was corn silage. This was a bit intentional just to try to keep things as constant as we could to evaluate that grass waterway addition, keeping as much of the system constant as we could. And then just highlighting what that waterway looked like. It was installed in the summer of 2020 to meet NRCS design standard. And next, I'll just highlight the phosphorus losses at this site. And I'm going to draw your attention to the darker purple, which is the particulate form of phosphorus, which is the form that's more associated with soil loss. So if we focus in on that darker purple, we again see from 2020 to 2021, a pretty dramatic drop in that particulate phosphorus. But this begs the question, are the reductions we're seeing because of that grassed waterway or something else, a difference in the weather pattern? So I'm going to turn things over to Ellen to highlight digging into this question a bit more. Were the reductions because of the waterway or something else?
Great, thank you so much, Lindsay. So like Lindsay just said, for the next portion of this talk, we're going to continue to explore those patterns you just saw and try to tease apart the effect of what the waterway did versus other confounding environmental factors. And we had reason to think that other conditions at this site might be influencing the losses that we were seeing. And specifically, we noted that annual precipitation varied over the course of the study period. So specifically for the 2 years of the study before the waterway was installed, it was abnormally wet conditions. And then for the years after the waterway, overall things were a bit drier. So we wanted to know, like, were we really seeing the effect of this waterway installation, or was it being confounded by some of the differences between wet and dry years? Since we expect wet years to have greater runoff and thus greater soil and nutrient losses. So our question was, were we seeing the effect of this waterway or more of a natural difference? And we set about answering this question using 2 different statistical methods. So the first method that we used is called an analysis of covariance, or ANCOVA. And in general, this method allows a user to test for a difference in some outcome or response variable of interest between 2 different groups, while controlling for the effect of some other variable that you don't necessarily care about, but it could be confounding the relationship that you do care about. So in terms of our work, we were interested, go to the next one, please. So in terms of our work, the response variables that we were interested in were the soil loss and the total phosphorus losses in surface runoff. And we wanted to know how those responses differed between events that happened before the waterway was installed versus events that happened after it was in place. But we needed to control for other environmental conditions. So specifically, we controlled for the covariate of runoff volume. And this is because we know that there's a relationship between runoff volume and soil and nutrient losses, with bigger runoff events being capable of causing more erosion and thus greater losses. So in controlling for runoff volume in this analysis, it helps us to better isolate the effect of that waterway addition. So let's look at those ANCOVA results, and we're going to start with soil losses first as our first response variable. So here we have a plot showing individual runoff events as those different points, and these were all the runoff events that happened before the waterway was installed. And these points are plotted based on the volume of runoff in that event along the x-axis, and then the associated amount of soil loss in pounds per acre on the y-axis here. And I'll just note that these axes are on a log scale, but the labels have been back transformed just to aid interpretation. So under the hood, the analysis fits a trend line to this group of data. And then it repeats the whole process for runoff events that happened after the waterway was put into place. So we can see here for both groups, there's a direct relationship between the amount of runoff that we have and the amount of soil loss for that event, with bigger events having higher soil losses like we'd expect. However, the after group, those events that happened after the waterway was put in, are shifted lower on the graph. And this means that for the same magnitude runoff event, soil losses were lower after the waterway addition. And ANCOVA is able to tell us that this is a statistically significant difference. And one of the advantages of ANCOVA is it allows us to compare runoff events of the same magnitude across these different groups. So just to walk through an example, if we look at the average runoff volume for this site, it's around 0.4 of an inch, where I've put that red arrow on the graph. If we look at that average runoff event, we can compare those two trend lines at that point. And it estimates that before the waterway, that runoff event would cause around 140 pounds of soil loss, pounds per acre. And then after the waterway addition, that same magnitude event would cause 3 pounds of soil loss, so a big reduction. So those were our soil loss results. We then repeated this process for total phosphorus loss as our response variable. So you're seeing the same sort of graph here, but just now with the total phosphorus loss shown on our y-axis. And similarly to soil loss, we found that total phosphorus losses were significantly lower for events after the waterway addition. So those were the results of our ANCOVA models. ANCOVA is a relatively simple statistical tool, so it was a really nice first cut at trying to get into the effect of the waterway. And seeing that there was a significant difference was a good sign that it was worth digging into this further with more complex methods that could better handle some of the nuances of this data set. So now I'm going to share the second statistical method that we used. And for these results, I'm going to focus in on just phosphorus as our response variable of interest. So the second method that we use is called a generalized linear mixed effects model. I know that sounds a little technical, but the main things to know about this method is that first, it allows us to better handle data that's not normally distributed, like the data we have. And then this type of modeling approach also allows us to account for some of the structure present in our data set. And specifically, we have this nice data set measuring runoff events continuously over the course of 5 years. But runoff events that happen closer together in time are going to be more similar than events that happen further apart. So if you have a few events around snowmelt time, those events are going to be more similar to each other than an event that happened in March versus July. So being able to specify some of that temporal structure in the model helps us to better meet the assumptions of that test and make sure we're using it correctly. So, specifically what we did for this model, our goal was to quantify the treatment effect of that waterway installation on phosphorus losses, controlling for a number of environmental variables. So we controlled for the amount of runoff, just like you saw in the previous analysis. But we added a couple additional variables. So we looked at whether or not the soil was frozen, how fast the runoff water was moving or its peak discharge. And then we used a factor describing the month and year that an event happened, like March 2019. And that was, how we controlled for the temporal structure in the data. Initial results from this modeling effort suggest that event total phosphorus losses after the waterway installation were around 25% of what they were before the waterway was put in, which is a convoluted way of saying that we saw roughly a 75% reduction in event total phosphorus losses. So the results that Lindsay and I have shared with you suggest that the addition of a grassed waterway in a concentrated flow path experiencing gully erosion can significantly reduce soil and phosphorus losses. However, given that these are results from a single site, it's important for us to acknowledge that we might not see the exact same outcome in a different location. So we just wanted to highlight a few characteristics of this site and this waterway that we think were particularly important in the success that we saw. And these are things to consider for other waterway projects. So first and foremost, this waterway was designed and installed according to the NRCS practice standard. So it was the correct size and shape to convey the water from that basin. And they also had good success establishing a vegetative cover over the entire waterway. This site also managed their infield erosion using no-till and cover crops. So this helps the waterway performance in reducing the sediment load that the waterway has to deal with in the first place. This also helps with establishing vegetation because that young grass isn't getting buried by sediment, so you can get good cover established. And then lastly, this farm has been able to properly maintain their waterway and adjust their field operations around it. And this last point is a lot easier said than done. Just to give an example, if an herbicide treatment is used on a field with a waterway, it requires planning and communication. So whoever is doing that application needs to have updated maps. They need to know where the waterway is. They need to know how to adjust their equipment and their route to not accidentally spray off the waterway. So yeah, certainly easier said than done, but really an important part of continuing good waterway function. So that wraps up our case study exploring how the addition of a grassed waterway was able to work with other in-field conservation practices to really well manage soil and phosphorus losses on a dairy farm in northeastern Wisconsin. And we'd like to take the last few minutes of this talk to highlight one more way that we're using Wisconsin Discovery Farms data to evaluate practices, this time at a broader geographic scale. So as a state, Wisconsin is in the process of updating its nutrient reduction strategy, which has now been rebranded as a nutrient loss reduction strategy. If you're unfamiliar, this is a type of strategic plan that's required of all states in the Mississippi River Basin, demonstrating how they plan to reduce the export of phosphorus and nitrogen from their state to the river. So updates to Wisconsin's strategy include the addition of what's referred to as a BMP science assessment. So this is a data-driven evaluation of different best management practices that can be used to reduce nutrient export from the land into surface waters. And Discovery Farms has been pulled in to look at agricultural BMPs specifically. And I'll just note here that this is a really big project with a lot of people contributing to it, and the Discovery Farms portion that I'll highlight is a small piece. So if this is interesting to you, I encourage you to check out the project website, linked here at the QR code, and learn more. So just to give a bit more detail on that science assessment that we're involved in, the overarching goal of it is to collate estimates of what we expect the effect of implementing different conservation practices to be on water quality outcomes. And specifically, water quality outcomes, I mean phosphorus and nitrogen losses in surface runoff. So a variety of literature and data sources are being leveraged to address this goal, including some of our historic Wisconsin Discovery Farms data. And specifically, we're using data from our surface edge of field monitoring stations. And this ends up being around 25 sites across the state over the last 20 years, as shown on this map. Our first goal with this project was determining what conservation practices we could actually evaluate with the data we have. There's so many agricultural conservation practices, and as rich as our data set is, we don't have every practice represented. So in thinking through the data we did have, we identified 5 practices or sort of categories of practices that we thought we could reasonably evaluate either at a case study level or more of a broad comparative scale. So for the case studies, we're going to look at grassed waterways, which is the preliminary analysis we shared with you all today. And then we also plan to look at cover crops from a paired basin study that was done a few years ago. And then on that broad comparative scale, we are going to look at 3 practices. So still a little undefined at this point, but we do plan to make some comparisons across sites with different tillage programs and across different aspects of manure and commercial fertilizer management. So this is still very much a work in progress, but we're excited that Discovery Farms is being used in support of this effort, and we look forward to sharing more results with you as we have them. And at this stage, we're also very, very open to feedback and ideas. So if any of this has sparked an idea for you, please don't hesitate to reach out. That brings us to the end of our talk, and we just want to end with 3 key take-home messages from the case study and sort of Discovery Farms work overall. So first, soil conservation and reducing soil erosion is a journey, and the critical first step really is protecting those concentrated flow paths where water's coming together and can have a lot of erosive power. A great way to protect a concentrated flow path is with a grassed waterway. A well-functioning grassed waterway has the potential for significant reductions in soil and associated nutrient losses. And these practices work really well when stacked or placed with other in-field practices to reduce erosion and nutrient losses. And then our last point here, thinking sort of more broadly about the mission of Discovery Farms, there are opportunities to use or reuse observational Discovery Farms data to evaluate practices. However, we have more power to attribute causation when we have more structured studies with a before and after, like you saw today, or even control basins. So something we're certainly thinking about as a program as we look to future projects. Just want to wrap up with a few resources that might be of interest, and we will also get links to these in the chat for you if you missed the QR codes here. Then we just want to end with a huge thank you to everyone who makes this work possible, our participating farmers, project partners, funders, and members of the Discovery Farm Steering Committee. Truly, this research would not happen with all these people, so a big thank you. And with that, here's the contact information for our Discovery Farms team, and Lindsay and I are happy to take any questions with the time we have left.
That was awesome. Thanks, Lindsay and Ellen, for your presentation. We do have a couple questions, so I think we can address a few of those. Also, I just wanted to point out, I've been looking through the participant list, and I have noticed that we have some current and even former Discovery Farm farmer participants, and I think they deserve a real shout out for spending their time with us, both for their monitoring sites that they're hosting, as well as listening to things like this today. So we appreciate you taking your time out, and it's good to see your names on the list. So the couple questions we have, let's just start with I think maybe some of the observational pieces that you all have, that you and Lindsay and Aaron have been able to gather by just being there and kind of visually seeing the changes of the site might help. So one of the questions is how much of those 2020 losses might be due to construction of the waterway?
The majority of those losses happened pretty early in the year around the snowmelt, March, April timeframe. So it was before the construction of the waterway, not much runoff after the waterway went in. So most of that was prior to the waterway work.
So the couple people feeling like the impact of that grass waterway is pretty impressive, sort of an unsung hero of our conservation practices, right? Is there still a concern about infield soil movement before it reaches the waterway? Sort of what have you seen observationally about how those practices are working infield compared to what the effect of the actual waterway itself might have been?
Yeah, I guess observationally, the site in particular actually has the most impressive cover crops we've probably seen at any of our Discovery Farm sites. Their cover crops, they're able to get like knee-high cover crops by the time the soil freezes each year. So their cover crops are working really well. They're using the no-till, so they thought they were doing all the right things. And it's an area of the field that it washes out every year. Not that bad, they thought. smooth it out. Maybe you need to do a little tillage over that particular spot, smooth out the field. So it's a spot they didn't think was that bad until the monitoring equipment went in and then they saw the numbers. So I think an important note to make is, yeah, if you're seeing a little bit of soil moving, see that erosion in a concentrated channel, the numbers are probably worse than you think it is, actually. And so in this case, the waterway really is what I think, in my opinion, did a lot of the work in reducing those numbers, because the infield practices have been working really well before and after the waterway went in.
Perfect. There's just a question about, could you repeat those numbers again? Have you seen anything in the literature that, or from any other sites that seem like to show the similar impacts of a grass waterway?
Yeah, it would be great to have another site with the same story, so we could get a comparison of before and after. I'd have to dig into the literature and see if there's any other studies like before and after. I do think it is, like you said, an unsung hero in the conservation world. It's not the shiny new like no-till cover crops we hear a lot about. So it's a little dustier on the shelf, but an important one to keep in mind. But yeah, we don't have any other sites where we've done the same work, so.
That wasn't supposed to be the story at this site either, was it?
No, it was not the intended start of the project, but it has taken over the story.
That's on-farm research for you, right? So a question from James Spicala. Does the eroded soil and phosphorus then reside in the waterway?
In this case, I think a lot of the erosion was happening from like the water cutting into the soil and digging the channel out. So infield erosion that would happen would settle now in the waterway, but I think in this case, the issue is more that there was a channel forming and the water was cutting that channel and digging it deeper and deeper and taking more soil with it as it did that. So by adding that waterway, I think a lot of the erosion has stopped, and it's not really like that 50,000 pounds is sitting in the waterway.
Awesome. Well, thank you, Lindsay and Ellen, again for your time. There are a couple more questions that are in the chat, but I think I would like to keep us on time. So you could go ahead and answer those in text for those. So as a participant, make sure you're keeping an eye on the Q&A box, both the questions that have been answered live, the questions that are coming in, and the ones that have had typed answers for them too. It's really nice to be able to have all of those options. So thanks, Lindsay and Ellen, again, we appreciate your bringing that information for us.
Thanks, Amber.
All right, so as we're transitioning to our partners from Vermont, we're going to launch a quick poll to collect some demographic information from you. This anonymous information helps us evaluate the audiences we're reaching with this type of work. So please fill it out, as it really helps our work. Also, just as a heads up, there'll be a question box at the end of the webinar that asks you about the value of today's webinar information. That self-rating also helps us improve future programs. So please take a moment to answer that before you leave the webinar. I know no one wants more surveys, but we really actually do use them. So our next speakers will be from the Discovery Acres and Discovery Farms program in Vermont, Claire Benning, Dr. Heather Darby, and Dr. Joshua Faulkner. Claire Benning started working on the Discovery Acres project as a research specialist this past September. She earned her master's in agroecology from UW-Madison, researching the benefits of cover cropping in organic dairy systems, and is currently pursuing a PhD in plant and soil science at UVM. Dr. Heather Darby is an agronomist and soil specialist with the University of Vermont Extension. She provides leadership on the crop and soil aspects of Discovery Farms research in Vermont. And last but not least, Joshua Faulkner is an extension professor at UVM who focuses on applied research and outreach on soil, water, and nutrient-related issues across the state, and providing technical assistance to farmers on practices and innovative solutions to improve the management of these resources. He also coordinates the Farming and Climate Change program in the UVM Extension Center for Sustainable Agriculture. Today, the title of their talk is Can Tile Drainage and Best Management Practices Help Vermont's Oversaturated Soils? Go ahead and take it away.
All right, thank you very much for that introduction. I'm gonna go ahead and share my screen. Amber, can you just give me a thumbs up if you got it?
That looks good.
Okay.
Yep.
Perfect. All right. Thank you everybody for joining us here today. My name's Claire. I'm with the Vermont team, and I'm going to get us started. First off, I would just like to thank our partnerships and funders, primarily the Lake Champlain Basin Program and the Vermont Agency of Agriculture, for their continued support and advice on this project. So to get us situated and kind of move out of Wisconsin and into Vermont, I would like to just kind of let you guys know that we are working in the Lake Champlain Basin area. So Lake Champlain is this nice big blue lake right here. And it is bordered pretty much by Vermont and New York. And then 16% of the land use in the Lake Champlain Basin is agricultural land. So all of the yellow that you see on this map over here is agricultural land. And in Vermont, dairy farming is pretty much our primary ag sector. It's roughly 65% of the total income in the agricultural sector. And fall manure application in dairy farming is typical practice in order to meet nitrogen requirements for our crops. This, however, unlike a synthetic fertilizer, overloads the field with phosphorus and leads to the accumulation of legacy phosphorus in soils. And up to 41% of total phosphorus loads to Lake Champlain is from agricultural production alone. This has led to seasonal harmful algae blooms starting roughly in 1970 and continuing through this day. So the challenges that we're looking at Discovery Acres in Vermont are centered a lot around our heavy clay soils, which are very, very poorly drained. This photo here is taken from a recent snow melt and rain event at our research site. And as you can see, it's pretty much flooded. And this drives the fall manure application because of excessive moisture in the spring. It's difficult for farmers to apply that manure prior to corn planting. Due to the poorly drained soils, legacy phosphorus is a primary driver of phosphorus loss through subsurface drainage in these systems. And shifting climates in Vermont have led to periodic snowmelt in the winter, rain on snow event, freeze-thaw cycles, and this increases the likelihood of nutrient loss during winter and early spring. And shifting climates have also led to increased heavy precipitation and increased flooding, which decreases crop establishment and yields and increases the loss of, or the risk for loss of nutrients in these dairy farming systems. So here in Vermont, we are looking at on-farm research trial that started back in 2020, 2021 in St. Albans, Vermont, in the northeast region of the Lake Champlain area. So it's just right here, smack dab in the center. And so we are really unique here in Vermont because we have 4 watersheds on one individual field in St. Albans. And we are really looking at what are the impacts of best management practices on water quality, crop viability, and soil health, and how do surface and subsurface flow contribute to water quality conservation efforts that are a huge goal for the Lake Champlain Basin. In order to address these questions, we are taking a paired watershed with edge of field monitoring approach, and we're comparing conventional management with best management practices, and we're comparing that with and without tile drainage. In order to look at the effectiveness of these treatments, we are measuring total phosphorus, soluble reactive phosphorus, total nitrogen, dissolved nitrogen, and total suspended solids in the water. And for soil health, we are taking routine soil fertility tests, pre-side dress, nitrate testing, soil health analyses through Cornell and their cache testing. And then for crop production and viability, we're taking cover crop biomass and percent cover, corn stalk nitrate tests, and corn crop yield and quality. So looking at our experimental field setup, we have 2 north watersheds and 2 south watersheds. For the rest of this presentation, when you see anything in this bright red color, it will be an indicator of our treatment in comparison to our control. So the north watersheds are our treatment watersheds, and they are where we are doing our best management practices. And we have one that is tile drained and one that is not tile drained. And then in the south watersheds, these are our conventional managements. Again, one with tile and one without tile. And what is really special and unique about our field here at Vermont is it does have just one field, has all 4 unique watersheds. It really is this undulating field where we can set up all of the edge of field monitoring systems, as well as these 2 tile systems in this kind of just really hilly environment. So when you're looking at kind of a cross section of our field, and when I'm walking up and down it, this is what I'm looking at. The timeline of our management events and our treatments kind of start in the spring, and everything is similar between treatment and control up until the fall, when we are doing manure injection for our treatment versus broadcast manure for our control and our conventional management. And then again in the spring with the cover crops, our treatment, we are terminating the cover crops by roller crimping and doing no-till planting. Whereas in our control conventional management, we are terminating the cover crops with tillage and herbicides as needed. So this timeline of management events has meant that the way that the years, the like calendar years line up doesn't exactly line up with our treatment years. So the baseline sampling was done in 2021 and 2022. Due to a drought in 2021, we extended calibration and baseline sampling into 2022. And then we started our transition year with that cover crop termination in that roller crimp versus tillage in the spring of 2023. And in the fall of 2023, we completed our transition year with the manure application, injecting versus broadcast. And so 2024, this past growing season, was our first full treatment year, and we are going to continue monitoring through 2026. All right, so I'm going to get into our weather and water quality data, and we're going to be looking at primarily results from baseline years as well as 2023 and 2024. I just want to reiterate, however, that 2023 is our transition year and 2024 is our first full year of treatment data. So looking at the weather for St. Albans, Vermont, we have all of the growing season months here for 2023 and 2024. And the average temperature in 2023 and 2024 were pretty standard to the 30-year average. What I want to really draw your attention to is the precipitation, which is the second set of values here. In 2023, we had a very, very wet year, especially during the growing season, with 3 extra inches of rain compared to the 30-year average. And then in 2024, we had a very dry fall and we had less rain during the growing season in comparison to the 30-year average. Looking at those precipitation accumulation throughout the year as well, we have the 30-year average here in yellow at 37 accumulated inches over the course of the year. 2021 and 2022, this green and this orange are our baseline data collection years, which were both below the 30-year average. As you can see, 2021 was our drought year and it was just 15 inches below the average. So we needed that extra year to kind of even things out. In 2023, that is maybe when you saw Vermont in the news for historic flooding. 43 inches of rain over the year was a lot for are very clay heavy soils. And then this past year in 2024 was a little bit closer to the normal, but we did have a very, very dry fall here in Vermont. So all of these precipitation values contribute to how we sample our water quality, get our water quality samples. So we have our north surface and north tile treatments up here on top, and then our control treatments in south and south surface down here below. In 2021, we did not have a north surface station. We added it in 2022 for that extra paired watershed comparisons. As you can see, looking at our transition year in 2023, there were way more samples in comparison to 2024 due to that heavy precipitation year. Throughout the year, we're also collecting base flow samples every 2 weeks to get that constant subsurface flow and nutrient loss through that. The subsurface runoff and surface runoff are when we sample during storm events. I will now turn this over to Joshua to go into our water quality data.
Thanks, Claire. All right, so we just have a handful of slides here that summarize some of our water quality data collection so far, and I'll just say as Claire mentioned, we only have 1 year of treatment here, so really we're just kind of looking at our observations thus far, and we haven't yet been able to perform any of those advanced statistical analyses that we hope to do in the coming years with more years of treatment. And the way we're going to present these today is that we've summed up loads for each of the weather years on pounds per acre per year, but we have a different number of samples for each of the stations. It's challenging to do this type of monitoring in northern states, as I'm sure some of you are aware of, with freezing and equipment malfunctions. So we inevitably miss an event here and there from some of the stations. So we've tried to normalize our load by the inches of precipitation per year. So what we'll look at today are actually pounds of a nutrient per acre per inch of precip. And so we're just in an effort to try to compare apples to apples across these little watersheds. And we're also just looking at storm event data and none of the base flow loadings for the tile sites. And I think this is generally okay. In some of our other monitoring work, we've seen upwards of 95% of, for example, phosphorus transport occurring in storm events and not in that base flow. So it doesn't appear to be a significant contributor on an annual basis to our loading. And we're not going to show those 2021 data because we only had 3 watersheds operational, and we're just missing. That was also a very droughty year. All right, Claire, you can advance to the next one. So we'll start with our total nitrogen loads, and just to orient you to what you're looking at here on your screen, we have vertical bars for each of the weather years, 22, 23, and 24, and then numbers above those bars are the number of samples collected within that year. And as Claire mentioned, the red boxes, the watersheds circled or outlined in red boxes, those are treatment watersheds, and the others are the control watersheds. And the other thing I want to note here is that on the far right of your screen, right of that vertical black bar, we've actually summed up the surface and subsurface loadings for each of the tiled watersheds. So you're looking at a combination of both surface and subsurface there on the right. So you can kind of compare that to the untiled watersheds and see the differences between total export from those. All right, so really just kind of 3 takeaways here that I want to highlight. One is that if you do the math and calculate total nitrogen losses from these watersheds for the year, you come up to somewhere between 15 and 35 pounds per acre per year. We do see less nitrogen loss from the untiled watersheds than we do from from the tiled watersheds. And this total amount of loss is actually, compared to some of our other data in other watersheds, this is pretty good. We've seen some losses of upwards of 60 and 70 pounds per acre per year. The other thing, the second thing I want to highlight here is that if you look at again, the far right here, right of that vertical black bar at the combined surface and subsurface bars, it's very clear that total nitrogen is higher from the tiled plots than it is from the untiled plots. This isn't unexpected. You know, we know that nitrogen in the form of nitrate is negatively charged and is pretty slippery in the soil and leaches readily. So we have this additional pathway of nitrogen loss in these tiled watersheds. So we do see greater nitrogen loss when we have tile. And the last thing I think I would highlight is that we have fairly high losses in 2022, and we're thinking about this or attributing this to the very droughty year we had in 2021. Not much denitrification, not much leaching in 21. And so then when we went into the winter of 22, we had a lot of nitrogen in the soil that was could be readily leached. And so we saw that come out in 2022. And then just again, as far as comparing control to treatment, it really, you know, we just have that 1 year of treatment. There's not much to say there, and not much that we can really see, no matter how hard we squint when we look at these data. You can go to the next slide, Claire. So here we're looking at total phosphorus, and again, these are pounds per acre per inch. So if we do the math on total loadings from these watersheds for the year, we're somewhere between 0.7 pounds per acre per year and 4.2 pounds per acre per year. This is a little bit higher than some of our other monitoring data. Some of our other fields have hovered right around 1 to 1.5 pounds per acre per year. And I will say, again, this is not comprehensive. Of course, we do miss a handful of events through the year, again, because of icing or equipment malfunctions, but this kind of shows us what our general range is in terms of total phosphorus losses. The other thing I'll highlight on this one is that you see surface runoff spiked in 2023 with a really heavy rainfall year that we saw that, and that was especially notable in the untiled plots, but not necessarily in the tiled plots. They, you know, as you might expect, those tiled plots remain better drained with that really wet year, and so I think we saw less opportunity for surface runoff, erosion, and surface nutrient loss in those tiled plots. And that's, you know, that was one of our guiding questions with Discovery Acres, is what is the net effect on phosphorus loss between a tiled field and an untiled field. We expected we would see more more surface loss, of course, in an untiled watershed. And so I think, you know, based on what we're seeing here, I think the answer to that question is it really depends, and it depends on the weather year. In 2023, we did see more phosphorus loss in those untiled plots, but then in the other years, it's really mixed. So we're excited to collect more data as we go here. Okay, let's go on to the next one, Claire. And then I'll just finish with soluble phosphorus. And these, any patterns or trends here look very similar to the total phosphorus on the previous slide. I really just wanted to show this to illustrate what percentage of our total phosphorus is soluble, and it's somewhere between about 40 and 50% of our TP is in the soluble form. And if you compare that to our watershed scale work, we're typically seeing 60% in rivers and streams in these agricultural watersheds. So this 40 to 50% is very similar to what we see elsewhere at the field scale. Now I'll go ahead and hand it to Heather.
Great, thanks, Joshua and Claire. So I'm going to dive into the agronomic data, and as has already been said by Claire and Joshua, this is just our first year of treatment data. And so we haven't really done rigorous statistical work yet. And, you know, not a ton of conclusions we can draw. I think importantly, as Joshua mentioned, and Claire too, this is a commercial site. You know, the field has been in rotation with corn and alfalfa grass mix. When we set this trial up and tiled the watersheds, it was coming out of alfalfa grass, and that was in 2021. So it has been in continuous corn since that time. And now, as already stated, we've started to deploy the best management treatments. So if you could go to the next slide, Claire. So here's a summary of the work that we've done in those different treatments in 2023 and 2024. And, you know, we're under the same, we're actually doing most of the management, even though it is on a commercial farm, trying to control things a bit and get, you know, work done timely. But we are at the mercy of the weather, just like the farm. And so, you know, we're having to do different treatments and practices when we're able to do them. So a couple things to note here, and we'll talk about it and you'll see it in the data, is that with the best management treatment, we're planting green in those north watersheds. And Claire had said that we were using a roller crimper, which we are, but we're going in when the cover crop is much larger, right around the time essentially when the farm would be normally planting corn, and planting green into that crop, and then rolling it down if needed. But herbicides are still being used. In the south watershed, the herbicides and cover crop termination is basically happening as the farm would do it, which is as soon as humanly possible. So there's no waiting on letting that cover crop grow bigger or build more biomass. Essentially, you know, as soon as we get that first break and the ground is dry enough on that heavy clay soil, the farm is out there spraying out the cover crop and then preparing the field to plant by using tillage. So a couple of really different strategies there. And then, you know, in the fall, which is when manure is commonly applied on these heavy clay soils, again, a lot because of timing. You never know when that field is going to get dry enough in the spring. People don't generally have time to get manure applied, so they're putting it on in the fall. And the treatments differ that way, where we're looking at injected manure on the north or treatment watersheds, followed quickly by cover crop planting. And then in the non-treatment south watersheds, we're just broadcasting the manure and incorporating it, and then also planting cover crops. And the timing of that, again, we're at the mercy of the weather. And so I feel like the project here, as it's meant to be, really reflects real management and real, you know, sort of challenges with the weather. Next slide, please. So we have been looking at soil health since the project was initiated. So even in those baseline years, we're collecting soil health samples, sending those off to the Cornell Soil Health Lab for their kind of complete assessment that they do. So we've been doing that since the project started. And now, of course, we're putting treatments into place, and we're looking to see if those treatments are going to make a difference on soil health. Again, not a ton to see yet, but we are seeing some slight differences where the BMPs are being implemented. We're seeing slightly higher aggregate stability, which would make sense. I guess before I move on, I had this in my notes and I forgot to say it, but planting green into a living cover crop and then spraying it out means that we're no-tilling, and I should have been clear about that. So, and that's a really important component and shift down here on this farm. Heavy clay soils. We have very few people in Vermont that are no-tilling with cover crops and planting green in Vermont. It's just very difficult, and farmers are very concerned about the risk of no-till in those heavy clay soils. So that's a big difference here. So you can see the aggregate stability in those treatment plots. Again, they're no-till with longer growing cover crops, seems to be a bit higher than those treatments in the south that are tilled with an early terminated cover crop. And I'm sure we'll continue to see more differences as time goes on. Next slide, please. All right, so if we're looking at tile drainage versus not, you can see that we seem, and again, this is very preliminary, no statistical analysis, but it does look like possibly the tile systems have slightly kind of lower soil quality in some aspects. And, they're more productive generally. And so that may actually be the case, better aeration as well. So we may see definitely different soil health indicators in those tile areas versus not, but time will tell. Next slide, please. All right, so one of the questions our farmers raise, because there's a lot of controversy about tile in Vermont and whether it's a benefit to conservation and water quality or a detriment. And so that was a big driving force for this project, to really understand how does tiling benefit and challenge farms and the environment. And what we've heard from farmers over the years is that when I have fields that are tiled, I'm actually able to implement conservation. I'm able to implement no-till. I'm able to get cover crops planted on time, terminated on time. I'm able to do more conservation on my farm and obtain better yields. And that's what we hear from farmers, but we don't have much evidence to support that, which is again one of the driving forces for this project. And we're starting to see that. Again, we haven't run statistical analysis on this, but if you look at spring cover crop yields and percent cover, our tile fields tend to have better establishment of cover crops. And again, that may have to do with the conditions for crop growth, right? You can see that the treatment cover crops are higher in biomass. And again, that's because they're terminated later. So we're planting green in the treatment. So you can see the cover crop biomass is much larger at the time of termination. So a couple of differences here. The tile seems to be allowing for better cover crop growth, probably at establishment and then into the spring. And obviously waiting later to terminate the cover crop is going to provide more biomass and cover into the spring. So we imagine we'll start seeing more differences in soil quality and probably water quality as well as time goes on. Next slide, please. Here's just some pictures. Again, same challenges that farmers have. These are very difficult soils to work with when they're really dry and when they're really wet. And as Joshua mentioned, or Claire mentioned, we had really wet year in 2023 and very difficult to get the cover crop established in the fall. Down at the bottom, you can just see how poor the growth actually was in the spring of 2024. It's out there, but wasn't looking great. And so obviously, if you're out terminating, early in the season, you're not going to have a lot of growth in these conditions, probably not a lot of impact on soil health either. But as we waited, you could see the cover crop greened up And the longer we waited to terminate that, obviously was having different impacts on soil and water. Next slide, please. So we did go out and take some pre-sidrous nitrate tests in these treatments. So if you're not familiar with that, it's a test that's taken prior to top dress to look at soil nitrates. And, you know, there's some interpretation that's used to essentially decide if more nitrogen is needed in the system. This is a really common test in Vermont because we have a lot of dairy farms and dairy manure, and it's hard to predict nutrient release from the dairy manure. So this is a tool that's commonly used. You can see in 2023, the nitrate levels, especially in that north tile, were quite a bit higher than in the other treatments. And in 2024, the nitrate levels were very similar. I'm assuming, again, you have to remember the manure here was applied in the fall. So with all the excessive rain in 2023 that followed into the winter, a lot of the nitrogen was likely probably leached out of the soil. So there was very low levels of nitrates at the time of top dress. So a level of 6, essentially 6 parts per million, would mean that the farm would need about 110 to 120 units of nitrogen to meet their yield goals. And indeed, the farm put on 110 units of nitrogen at the time of top dress to the whole field, since it was so similar. Next slide, please. So this was interesting to us, what happened after that. And, you know, overall, what we're seeing is that the stock nitrate levels in the tile treatments are higher, okay? And cornstalk nitrate tests are taken at the end of the season, right before harvest, really, to measure accumulation of nitrates in the lower portion of the plant. And that's an indicator of if the plant had sufficient or excess nitrogen by the end of the season. So you can see in the north tile watershed, those corn plants had an excessive amount of N uptake and it exceeded what was required for crop yields. And this is interesting, again, because the nitrate levels were all similar across all the plots, and they were all fertilized the same. And you can also see in the south tile, definitely wasn't as high, but was higher than in the surface plot of the south tile, of the south watersheds. So something is happening here. It makes sense. We're assuming with tile, the drainage is better. And possibly the plants are growing bigger and also more efficient and better able to take up nitrogen, but time will tell. So hopefully we'll be able to reduce nitrogen inputs by in our tile fields over time. Next slide, please. Okay, so we also looked at yields, and again, it's hard to draw many conclusions here, but I do want to know what was exciting to us was in the in the north tile versus surface, and in the south tile versus surface, or tile versus no tile, we're maintaining yields under no-till. So when you look at the north tile treatment, those are now in no-till. Cold turkey, right? Went from being in continuous corn to being in no-till on heavy clay soil for the first time in 2023. And so you can see the significant yield difference. In 2023, we had over 20 tons of corn, and probably one of the worst years on record for most farms with excessive rain. But where we didn't have tile, we only had 11 tons. And so in that excessively wet year, With no-till and tile, we were able to achieve really good yields on that farm, which was quite exciting to us. Now in 2024, we had a much better, more regular season, and you can see there wasn't as much difference in the north surface versus the north tile. Both of those were no-till, but again, you know, a better season, not as much rain, not as much saturation. We saw adequate yields in both. One thing I want to point out is in the south tile in 2024, you can see we obtained really good yields, again, over 20 ton, which is very good, especially on clay soil. But where there was no tile in 2024, you can see there was a substantial yield reduction. And part of that actually had to do with the fact that the ground was completely saturated in the south surface without tile in the spring when we planted. It was very, very wet. And we actually couldn't plant part of the field because there was standing water. And again, this is reality. In the tile field with tile, the farm was able to plant the entire area and as a result achieved much better yields. So more time will tell how these treatments will play out, but it's exciting that adding tile into these very heavy clay fields is allowing farmers to be able to no-till without significant crop loss. Next slide, please. And I think I'm turning it over to you, Claire.
Yep, I can wrap it up. We're a little over time, so I'll go quick. Just for some conclusions and next steps, our water quality data, like Joshua said, there are no obvious trends from our first full year of treatment data, and any of those small differences that we're seeing are likely weather driven due to 2023 being so dramatically wet and then 2024 having a really dry fall. The thing to note though was that the soluble phosphorus was around half of our total loads. And then for the agronomic data, the best management practices are having positive effects on soil health indicators, and tile drainage and best management practices can improve cover crop yields even in those wet years. And that there, like Heather just mentioned, there is no difference between the corn yields from the no-till and the conventional management, which is really promising in these systems. And our next steps for the Vermont Discovery Acres project will be continued monitoring of the crop productivity, water quality, and soil health measurements that we've been taking. And I'm going to begin the statistical analyses. And so that hopefully next year we'll have some more conclusive evidence for you. I don't think we have time for questions, but if anybody wants to grab our information, please feel free. And that is all we have for you from Vermont today.
Well, thanks, Claire. Thanks for wrapping us up with those conclusions. Thanks to Dr. Darby and Dr. Faulkner for all of you providing all of that for us today. I like the infusion of the agronomic and the water quality. That's a nice piece to bring them together. If you guys wouldn't mind answering the questions that have come into the Q&A
Sure.
just with typing, that would be fantastic. And then if we have some time at the end, we might kind of go back through some of those questions, even if they have been answered with typed text, because there's been some really good questions. So thank you guys again. All right, our next speaker is Tim Raditz. Tim works as the Discovery Farms Minnesota coordinator. His talk today is titled Edge of Field Water Quality Impacts of Cover Crops in Northern Corn and Soybean Farm Fields. Tim, looks like you need to swap views. I'm seeing your presenter view. There you go, looks great. Can't hear you if you're talking, might still be muted.
Yes. figure out this technology eventually. All right, now can you see everything?
Yep, that looks good.
All right, thanks for having me today, and thanks for that introduction, Amber. My name is Tim Raditz. I organize the Discovery Farms Minnesota program for the Minnesota Agricultural Water Resource Center. Today, I will be talking about Edgefield water quality data that we have collected throughout our program, and in particular, focusing on a site where we are evaluating cover crops in Minnesota. Before I begin, I want to give some shout outs and acknowledgements for the work done on this project. I'm the one up here talking to you today through the computer screen, but I actually don't do most of the work. I want to acknowledge the Minnesota Department of Agriculture. We partner with them on all of our Discovery Farms projects, and in particular, Scott Madison and Katie Rasmussen, who worked up all of this data that I'm going to show today. Also want to thank Reed Christensen, also with the Minnesota Department of Agriculture. He worked up the paired basin statistics that I will present toward the end of the talk. And I want to thank our primary funders for this work, the Minnesota Corn Growers Association. Without their financial commitments to our program, we wouldn't be able to share this exciting work with you today and do our Edgefield monitoring work that we do across Minnesota. Lastly, but certainly not least, I want to thank Kurt Trost, who I saw was on this webinar today as well. He is the one that actually farms the project that we're going to talk about later in the presentation. So his dedication to this project and our program is essential. Without our farmers and without them allowing us on our land and opening up, not being afraid of collecting this sort of data, we wouldn't have anything to learn off of. So those are all the things I wanted to mention before we dug in. All right. So I wanted to give a little background on our Minnesota program and data before we get into the cover crop project. We have worked with 14 farms throughout the state with our automated monitoring equipment. So we collect data 365 days a year, automated sampling, automated flow monitoring. We use flow-based sampling and looking at sediment, nitrogen, phosphorus. We cover a diverse landscape from the coulees of southeast Minnesota to the beach ridges of northwest Minnesota. Minnesota is just a very diverse state in terms of landscapes, and it's I think that's one of the fun parts of my job is getting to know all these different landscapes and how they impact some of the water data that we're collecting. We also covered a diverse set of agricultural enterprises, from corn and soy, cash grain farms, to dairy, to swine, to beef, to poultry. So we've kind of run the gamut in terms of all the different sorts of ag enterprises that we've monitored. As of this year, we are working with 5 farms, one in Stearns, Wright, McLeod, Redwood, and Waseca counties. The one I'm going to focus on later in this presentation is our farm in Redwood County. And so with this very diverse data set, it really helps us understand Edgefield runoff and tile drainage in Minnesota, especially in our agricultural areas. These next few charts will summarize all the data that we have collected over the years. This slide focuses on water volume leaving through either surface runoff in the orange box or tile drainage in the blue box. This chart depicts annual runoff in box plots. Box plots are a good visualization for this data set because of the vast differences from site to site and year to year. This tends to lead to a lot of variation in the data that we collect. The middle line depicts the median or 50th percentile. The upper part of the box is the 75th percentile, and the bottom part of the box is the 25th percentile. The X and the number in the box represent the average for the data set. So annually, on average, we see about 2.5 times as much water leave the field through tile drainage compared to surface water runoff. If we compare this to the amount of precipitation the field collects, this adds up to approximately 23% of the precipitation leaving the field, 17% in tile drainage, and 6% as surface runoff. Another way to look at this is, on average, we're retaining 77% of the precipitation on our farm fields that we've monitored in Minnesota. If we look at when this water is moving for tile drainage, it mostly moves during the growing season. We can see 88% of our tile flow is during the non-frozen soil period. Surface runoff is more evenly split between frozen ground and growing season, where it's about 50-50. And snowmelt is a very important hydrological process in Minnesota. The last few years withstanding where we haven't had much, but there's years where it's been 100% of our runoff on an annual basis, and there's years where it's been 0. So it just depends on year to year, but on average, over the last 14 years that we've been doing this work, it winds up being about 50% snowmelt and 50% rainfall induced runoff. If we dig further into the timing of runoff and tile drainage, we can see that most of the flow occurs in the March through July time period. Even though we are monitoring year round, most of the work is in the early spring to crop canopy period. After the crops become canopied, the amount of water to monitor becomes less. Moving on to soil loss, this chart depicts annual soil loss for surface runoff and tile drainage. As you can see in this graph, almost all of the soil loss that we monitor is carried by surface runoff, and this primarily happens during the growing season. We see 95% of our soil loss come when our soils are not frozen. In fact, if we look at our monthly soil loss data, we can see that almost 70% comes during May and June. What happens during May and June? Well, it's a combination of vulnerable or bare soils and more intense rainfall events. So what this tells us that if we want to reduce soil loss, we need to focus on providing soil protection during the months of May and June. And this can be the most challenging time to provide that protection as we are trying to establish crops, but it can be done with increased residue or limited tillage, cover crops, and perennial crops. These are all good ways to provide some more soil protection during that critical time period. Moving on to phosphorus loss, this chart depicts total phosphorus loss on an annual basis throughout all the sites in our program through surface runoff and subsurface tile. We can also see that almost all of the phosphorus movement through this is coming through surface runoff compared to tile drainage. This loss is split between frozen soil or snowmelt and the growing season. What's unique and challenging about phosphorus movement is that about half is attached to soil particles as particulate phosphorus, and the other half is dissolved in water. Traditionally, it was thought that most of the phosphorus movement in agricultural fields was attached to soil particles, but there is a significant portion of dissolved phosphorus that we have monitored. Many of our conservation practices used to prevent soil loss and in turn particulate phosphorus loss do not impact dissolved phosphorus loss, and in some cases increase dissolved phosphorus loss. Now I could do a whole talk on this issue, but nobody has time for that at the moment. But what we have learned from the work we have done is that we need to try to incorporate our phosphorus from fertilizers and manure below the soil surface. That will decrease dissolved phosphorus loss. However, when we do that, we need to incorporate without creating too much soil disturbance in order to protect the soil surface from excessive soil loss. The combination of both soil protection and incorporation of phosphorus from fertilizers and manure is the sweet spot for managing phosphorus losses. Lastly, we'll move on to nitrogen loss. This is a graph showing the total nitrogen loss on a pounds per acre basis for our tile sites in blue and our surface runoff sites in orange. This is where the story shifts from soil and phosphorus loss. The graph, as you can see, most of the nitrogen loss that we observe is through tile drainage. This makes sense as nitrate nitrogen is negatively charged and it moves freely with water in the soil profile. So as water infiltrates the soil profile, nitrate can move freely with that water. Most of the nitrogen loss in tile drainage is during the growing season, almost 90%. And it is in the nitrate form. So if we're looking at tile nitrogen losses, we're looking during the growing season and looking at nitrate. If we plot up all of our data, we get a strong relationship. If we're looking at nitrate loss on the y-axis versus tile drainage on the x-axis, as the amount of volume of tile drainage increases, so does the amount of nitrate loss. This makes sense because the more water that moves, the more nutrients that move with that water. Ultimately, we have limited impact on controlling the amount of tile flow, as Mother Nature and the amount of rainfall are the primary driver for the amount of tile flow. What we do have impact on is the concentration of nitrate in that soil profile available to move with that tile drainage. You can see some scatter in this relationship around our linear regression line, and this is due to changes in nitrate concentrations. So if we're on the higher side of this line, we have higher concentrations in our soil profile compared to if we're on the lower side of this line. On average, we lose about 4 pounds of nitrate for every inch of drainage that we've monitored in Minnesota. So after that brief context of water data that we have collected throughout the state, I want to shift to talking about our cover crop project in Redwood County. We started this project in Redwood County with the goal of getting good edge of field water quality data on cover crops. We get so many questions about the benefits of this conservation practice in Minnesota. And so our main goal and our main questions that we wanted to answer is, how do cover crops work in Minnesota on a privately owned cash grain farm? And how do they impact water leaving those fields? And this ended up being a really great setup for looking at those questions. This would be an overview of the site we're going to be looking at. We have one field that we're monitoring and 2 basins within that field. We have a north basin and a south basin. The north basin is 12.2 acres and the south is 10.2 acres. We are doing surface and tile monitoring at each of these basins. The crop rotation is a corn soybean cash grain rotation. We have some loam soils, 3% slopes. And we started monitoring in 2018, actually in 2017, but that was sort of a partial year. Our first full year of data collection was in 2018. And we run all of our data on water years. And this water year runs from October 1st through September 30th. So if I'm talking about water year 2018, that's October 1st, 2017 through September 30th, 2018. We had a calibration period in water years 2018 through 2020, where we had identical management on each of the north and south basins. So everything was operated the same during that calibration period to collect some baseline data so that we could implement a change and then use some statistical methods to see if that change was having any impact on the water that we were monitoring. So after harvest in 2020, we moved into our treatment phase. So that would be water years 2021 through 2024. Again, identical management on this field in these 2 basins, except for the cover crops. During this time period, we had a cover crop on the north basin and not a cover crop on the south basin. Other than that, the ag management practices were the same. I was able to do a little art project last night when I was trying to get myself to understand how the ag management practices differed for this site. So if we're looking at our calibration period, all of our farming practices in the north and south basins were the same. So this whole period, both basins were farmed the same. So in 2017, there was actually in the summer of August, there was a cover crop flown on, and cover crop comprised of annual rye, radish, and clover. We didn't have any germination, and this was sort of a reoccurring theme throughout our project. And I should have Kurt really talk about this because he is the expert on this and knows much more, and everybody would be much more entertained by him talking about it than me. But I am here. So he struggled with the aerial application of the cover crop in this system, and The timing of that was always in August. Part of the struggle with getting anything to catch with an aerial application was the crops that he was required to use as part of his whatever program that he was in. It was like an annual rye, radish, and clover mix. We really had a hard time getting germination out of that mix in this cash grain, corn, soybean, more of a traditional cash grain sort of operation. There just wasn't enough time. There wasn't enough, didn't get enough soil contact with these seeds to really get much or any germination. So as we moved in from 2017 to 2018, there was some shallow disc or vertical tillage. Corn was planted, and then there was another aerial application in August of 2018 of that same cover crop mix. Kurt wanted to see if a different type of crop would make a difference in terms of our results for getting a cover crop to grow. So another flight happened where winter rye was flown on, or winter perennial rye. Had much better results with this. We actually had some germination and cover crop moving into the next spring. So as we move into 2019, again, a shallow disc or vertical till moving into soybean planting, and then another aerial application, no winter rye this time, and no germination. So having some issues, and I think primarily mostly because of the type of crop seed that we were trying to get established. But as we moved into 2020, this again was our calibration period. We had some tillage, grew some corn. Once we harvested that corn, then we started our treatment phase of the project. So as we move into the treatment phase, again, the North Basin had cover crop, the South Basin had no cover crop. So on this infographic, all these things would be the same for the South Basin, except for there would be no cover crop. Also in this period, he transitioned to doing more of a broadcast seeding after harvest, and then incorporating that seed with a shallow disc tillage or vertical till. So after the corn was harvested in 2020, again, a broadcast winter rye application with incorporated by a shallow disc. We were able to have some good growth. We had 812 pounds per acre dry biomass on that field in the spring of 2021. He did plant green his soybeans into that cover crop and then terminated the cover crop. And so planted into the cover crop, raised the soybeans, harvested the soybeans. After harvest, again, broadcast and incorporated the winter rye. Did get some cover crop growth the next year. Did terminate the cover crop and do some tillage before planting corn, but then harvesting the corn, broadcasting winter rye, vertical tilling it in, getting some good growth the next spring, planting green into that cover crop in 2023, and then harvesting soybeans, planting another cover crop after harvest, moving into the next year, good growth, tillage before corn planting, and then finally harvesting that corn, and that takes us up to date in terms of the ag practices. So this is a pretty typical establishment of cover crop. We can see the North Basin on the left and the South Basin on the right. The North Basin, this would be in the fall of 2023, and then in the spring of 2024. So for our climates and these corn and soybean rotations, this is a good catch for us. Just with the limited time in the fall after harvest to get this cover crop growing, this is pretty standard for what you're going to see is in terms of a success. So I know, with other crops, if you have corn silage or if you're doing wheat or some other crop where you have more time in the fall, or maybe you live further south where you have more growing season to deal with as well, you might have much better results. But in this sort of setting with these cropping practices, this is a success. We're able to do biomass surveys from 21 through 24. So again, just to get a feel of the different cover crop growth in the spring before termination. We always did this in the last 4 years. Actually, I shouldn't say we, I should say Scott Madison was able to do this. So this is all his data that I'm talking about. But in 2021, we had 812 pounds of dry biomass. 2022, here's some pictures. Again, this is just the North Basin. On the South Basin, there wasn't any cover crop. But we had less dry biomass in 2022 before termination. A little more biomass in 2023 before germination, and then 2024 had a little bit higher, yet had really nice green, more uniform coverage to that cover crop on the North Basin. So as we get into looking at the data generated at this site, this is just the annual precipitation. And again, we split our treatment phase, went through 2020, and then 2021 was, or I'm sorry, our calibration phase went through 2020. And as we got into 2021, that was when our treatment phase happened. And usually what happens with these sorts of projects and dealing with real sites in the real world, I think they're very powerful, but also very challenging, because as soon as we implemented the treatment, our rain just cut off. And it's extremely frustrating to say, well, we got this great comparison out there in terms of agronomic practices. Well, that's awesome, but if you don't get enough rainfall to actually generate runoff or much tile flow, you're not going to see any differences due to that practice. So while that is, as a researcher, extremely frustrating, I think it's also really important to know that not every year these things are going to make a difference in terms of water quality. It just depends on year to year and site to site and in the weather characteristics that you're going to see. Minnesota has this cool, the state climatology office has synthetic data from gridded database, so you can go into and put in your location and actually see a precipitation record back over 100 years, and kind of see where your annual rainfall ranks in terms of a really long precipitation record. And what's interesting, our site was active just in this portion of the precipitation record, but we were able to monitor the number one year. 2018 was the number one year on record for precipitation in this location. We are also able to monitor some very dry years, which I kind of talked about in the previous slide. So I think it's frustrating as a researcher to get sort of this variation, but also in the real world, this stuff happens. So very interesting to me to kind of understand how weather patterns impact everything as well. If we're looking at the amount of tile drainage, again, we're splitting here in 2020 between the calibration and the treatment. This is looking at subsurface tile in inches, and the north and south basins are plotted in bars for each year. So for this, we're kind of looking to see if there's any repeatable patterns going on. It looks like the south has a little bit more tile drainage in the first 2 years, not so much in the third year. And then as we get into 21 through 23 or 24, the results are more mixed as well. We're looking at surface water runoff. Again, same setup. We got the north and south basins plotted up for every year. Calibration, split this graph by calibration and treatment. Looking for any interesting patterns that show up, not really. One interesting thing I'd like to point out, and I talked about the importance of snowmelt runoff earlier, is this light blue bar would be snowmelt. So in 2020, 2021, 2022, and 2023, essentially all of the runoff that we monitored at these sites was snowmelt runoff. So again, that snowmelt portion can be very important. For 4 years, it was very important. Then we move into 2024, and then we had no snowmelt runoff, and everything was during the non-frozen ground period. So while that snowmelt period is extremely frustrating and challenging to monitor, if we didn't monitor it, we would miss 4 years of data at these sites. Looking at total suspended solids, this would be a measure of sediment loss. at this site. Again, same setup in terms of bar graph. We have north and south for each of these sites, and split by calibration and treatment. Again, no real pattern between the north and south basin, but a good thing to kind of note is the variability in the soil loss, where we can go from very high in one year to almost non-existent in the other year. And we can have years and years, or 3 or 4 or 5 years of non-existent soil loss, and then it'll pop up. So very episodic in terms of when we see soil loss. And if you remember that chart I talked about before, that May-June time period, essentially, if we don't get intense rainfall during that time period, our soil loss numbers are going to look really good. I think in 2018 and 2014 is where we saw some runoff during those time periods, and we're able to generate some soil loss. Looking at our phosphorus loss, again, this is surface only, and I'll go back to the soil loss. That was surface only as well. If you remember, most of our soil and phosphorus loss comes through surface runoff and not tile drainage. So that's sort of what we're focusing on here when the data I'm showing you. But again, phosphorus loss, there are some years with higher, there are some years with lower, and no real pattern between the north and south basins, and a lot of variability from year to year. If we move into nitrogen yield, again, this is just the tile data. We're looking at annual nitrogen loss on a pounds per acre basis. We have our calibration years on the left here and our treatment years on the right. This is sort of where we start to see a little bit more patterning, where we see the north is typically higher or lower than the south, except for this year. And then as we move into the treatment phase, the north was typically lower than the south as well. Where I think this comparison really starts to get interesting is if we look at the total nitrogen flow weighted mean concentration of our tile data. So these are annual flow weighted mean concentrations in milligrams per liter for our calibration period. And you can see these numbers are all very similar, which is good. They're pairing up nice. And as we move into our treatment phase, this is where it gets interesting. The first year we had very similar concentrations as well. And again, this is where we had cover crop on the north site and no cover crop on the south site. But as we moved another year into that treatment phase, we started to see some differences in nitrate concentrations in the tile, where the north, the spot where we were having cover crops. So this is what we're hoping to see. We're having some reductions in nitrate concentrations due to that treatment practice. And this also becomes apparent if you plot up all of our tile nitrate samples throughout the study period. For our north sites is in the blue. Again, our calibration phase, all the same practices. And in the blue, our north sites, so the blue dots had our cover crop, where the south sites did not. You can see they're overlapping each other during the calibration phase. As we move into 2021, a lot of overlapping yet, but as we move into 2022, we see some separation between the north and south, and that's what those annual flow weighted mean bar charts are showing us, is there is something happening there. So next, finally, I'll move into the slope statistics for the cover crop trial. This is the work that Reed Christensen put together, and I'm just up here talking about it. But you can look up the premises. We're developing a linear relationship between the two locations, so between the north and south basin, before or during the calibration period, and then during the treatment period. And so if that linear relationship changes, we can determine a statistical difference. And if you're interested in looking at some of the sources and resources for this sort of trial, there's some good links here for you. So if we're looking at annual water loss for tile and surface, here's where we start to see some differences due to the cover crop. The annual tile losses in inches, we're looking at our treatment watershed on the y-axis versus the reference watershed, so the watershed that doesn't have cover crop on the x-axis. So there was a significant trend, and the intercept, the shift in the line is significant. So that cover crop did reduce the amount of tile drainage during the years we were monitoring. So we're seeing a 45% reduction. If we look at surface flow, there is a significant trend, but there's no significant difference. So we weren't having any impact on the amount of surface water runoff during these last 4 years due to the cover crop. Other annual parameters, we didn't see any significant differences for sediment and phosphorus, and I think this has a lot to do, not that the practice wasn't doing anything, but I talked before about how episodic and how variable some of our soil and phosphorus losses can be. So depending on the year to year and these sorts of site designs, because we're dealing with real farms and real weather conditions, we might not have the conservation practice working when we're seeing some of these higher sediment and phosphorus losses. And that might be why we didn't see any significant differences in sediment and phosphorus loss. Nitrate yield from tile is significantly different. So we had a different intercept during the treatment period, which would be the blue, compared to the calibration period, which would be the orange. The statistics said about a 53% reduction. Our flow weighted mean concentration, that would be the FWMC for nitrogen from the tile. We didn't have a significant post-treatment trend, but I think a lot of it was due to this, maybe a lag in the treatment having an impact on the nitrate concentrations in the tile. That first year, that 2021, this is that dot here where it kind of more closely lines up to the calibration period than the treatment period. So we're going to continue on this work to actually see if we're having an impact on nitrate concentrations in tile. So we are reducing nitrate yield, but right now all we can say is we're reducing that nitrate yield because we're reducing the amount of tile flow due to that cover crop. So just to wrap it up, sediment and phosphorus, we need to focus on surface runoff based on the data that we've collected. Nitrogen, we need to focus on tile drainage. Cover crops in cash grain rotations in Minnesota, in northern climates. We had better luck with broadcast and incorporate of that seed after harvest compared to aerial seeding when that crop was growing. And winter rye was really king. If we had winter rye in that seed mix, we had a much better shot at getting some establishment. And even though the establishment wasn't what some people would consider significant, we did show some water quality impacts due to the cover crop. We reduced tile flow and consequently we reduced nitrogen loss. I think we might also see an impact to nitrogen concentration in the tile. We just might have a delay in that impact due to the cover crop practices. So with that, I think I can stop sharing. And if there's any questions, I'd be glad to take them.
Thanks, Tim. It's interesting to see how the nitrogen results from different states are starting to kind of stack up for the case of getting something green and growing in that fall time period, especially since we're so cold up here. I don't see any specific questions for you. There is one that I think is for Vermont about tile drain systems and comparing agronomics. So make sure that if you have questions for Tim, that you get them into the chat or into the Q&A box, and he can either type them, or it looks like we maybe will have a few minutes at the end that we could revisit. So thanks for that, Tim.
Thank you.
Keep an eye on the Q&A box. All right, so our last speaker today will be traveling south for a session from the Discovery Farms Arkansas program. Today we have James Burke with us. James works with Arkansas Discovery Farms projects across the entire state focusing on topics ranging from sulfate in runoff to biochar and soil health. His talk today will focus on the assessment of biochar as a soil amendment in eastern Arkansas agricultural production. Go ahead, James.
Okay, thank you, Amber, and thank you everybody for attending today's webinar. As you said, my name is James Burke. I'm a program associate for Arkansas Discovery Farms. And although my project is focused on biochar, the Arkansas Discovery Farms program has projects throughout the state of Arkansas, ranging from edge of field runoff to the effects of poultry litter in row crop agriculture. And also we're investigating carbon sequestration from a various wide range of farms, from row crop, livestock. We have a forestry farm in southern Arkansas, and we also have 2 horticulture farms in central and western Arkansas. So even though I'm presenting on one project, the program is investigating a wide gamut of projects throughout the state of Arkansas. The Arkansas Discovery Farms program is currently conducting biochar research in 3 locations in eastern Arkansas. The first location is in Newport, the second location is in Stuttgart, and the third location is in Dumas. In Newport, which is located in Jackson County, Arkansas, this project is being conducted at the University of Arkansas Division of Agriculture, Jackson County Extension Center. Stuttgart is located in Arkansas County, Arkansas, and this is a privately owned operation owned and operated by Mr. Terry and his son, Trent Dabbs. In Dumas, this project is being conducted on another privately owned farm owned and operated by Wes Kirkpatrick. Dumas is located in Deshay County, Arkansas. This biochar project was endowed from a grant from the Natural Resources Conservation Service. This is a conservation innovation grant scheduled to proceed for 3 years. This project started in earnest in January 2023 and will go until January 2026. The overall objective of this biochar project is to gauge and quantify the effect of soil-applied biochar on soil water pressure to make inferences to soil moisture retention along with other associated soil health properties. For those of you who don't know or are unfamiliar with biochar, biochar is pretty much a charcoal-like substance that is typically nutrient-rich. It is created in a process called pyrolysis, in which organic materials are combusted in low to no atmospheres of oxygen. Biochars can be made from a wide range of various organic resources. Resources such as crop residues, wood species, such as hard and softwoods, or especially relevant around here in Northwest Arkansas, poultry litter can all be used to make biochar. In the literature, you can find that biochar has been known to promote facets of soil health. Facets such as soil nutrient content and retention, retaining moisture in the soil, and the enhancements in soil structure and increasing pore space in the soil have all been attributed to soil applications and additions of biochar. Main justifications for this biochar research stems from irrigation concerns which are prevalent in eastern Arkansas agriculture. The main concern in eastern Arkansas agriculture is that regional aquifers are being depleted faster than they are being recharged. In eastern Arkansas, row crop agriculture dominates, and a good deal of these crops require a substantial amount of water to ensure proper growth and development during a growing season. There are also concerns regarding crop fertilization. As many of you all know who are monitoring edge of field runoff, nutrient losses due to surface runoff is a main concern, not only in Arkansas, but in various states as well. Also, fertilization concerns involve the increasing cost of fertilizer products, such as urea and potash. And finally, nutrient loading and pollutant capabilities of nutrients such as nitrate and phosphorus are of main concern in eastern Arkansas and Arkansas as a whole. In addition, soil moisture retention is becoming ever more prevalent in agricultural and soil science research. This table displays the biochar project experimental site information. In the first column, we have our closest city. Our farms are located near these cities. Some of these farms are located in really isolated regions, but for the purposes of this presentation and reporting purposes, I'm just identifying these farms by their closest city: Dumas, Newport, and Stuttgart. The second column is the county in Arkansas they're located in, The third county is the crops they are growing throughout the years of this project, 2023, 2024. I haven't shown crop information for 2025, but I just received it right after I produced this presentation. In Dumas for 2023 and 2024, cotton has been grown, and I just found out that in 2025, corn will be grown in this field at Dumas. In Newport, soybean will be grown in all 3 project years. And in Stuttgart, soybean was grown in 2020-23, corn was grown in 2020-24, with oat being grown as a cover crop from 2024 to the spring of 2020-25. And at Stuttgart, in 2020-25, the owners will revert back to growing soybean. The biochar used in this project was acquired from EnviroPack LLC. This is a full-scale facility dedicated to biochar production located in Monticello, Arkansas, which is located in southeast Arkansas. This biochar is primarily made from regional softwoods such as pine, which are prevalent in southeastern Arkansas. As you can see here, here's some chemical compositions of this biochar, which has a pH of around 9.5. The biochars made from this facility are available for research, industrial, or personal use. The cost of this biochar is approximately $260 per international bulk container. And this facility can tailor the biochar texture to your proposed use. The experimental design of this project consisted of 3 treatments: a no-apply biochar control, which I labeled 0B, a biochar rate equivalent of 2,000 kilograms per hectare, which I labeled 2B, and a biochar rate equivalent of 4,000 kilograms per hectare, labeled 4B. The experimental design was laid out in a randomized complete block design with 3 treatments and 4 replications or blocks. Each plot contained 4 rows, and each row was 10 meters in length. Between each of the treatment blocks was 3-meter alleyways in order to separate the treatment blocks. The biochar was broadcast on the soil approximately 1 week before planting at all 3 locations. Plot rates were calculated based on row spacing for the farmer's preference at each farm. At Newport and Stuttgart, row spacing was determined to be 75 centimeters, and at Dumas, row spacing was determined to be 95 centimeters. The row spacing value was extremely important in calculating biochar rates of application. And with the biochar was soil incorporated during each farm's planting event. Soil water pressure sensors and data loggers were installed at each farm. These soil water pressure sensors collected soil water pressure at soil depths of 15, 30, and 45 centimeter depths. In addition, bulk density samples have been collected in February 2024, and March of 2025. To analyze the data, I used 3 fixed effects: soil water pressure, soil nutrient status, along with cation exchange capacity, and bulk density. The random effect was replication in block for soil water pressure, soil nutrient status, and cation exchange capacity, and sampling year was used as a random effect for bulk density. For soil water pressure, I used a generalized regression model in JUMP Pro 18 using a negative log normal distribution based on soil water pressure having negative values. Soil water pressure is measured in units of kilopascals, and I set thresholds at -1 kilopascal to -230 kilopascals. Soil nutrient status, cation exchange capacity, and bulk density, I used a generalized linear mix model in JUMP Pro 18 and a log normal distribution. This first table displays Dumas soil water pressure by biochar treatment for all sampling dates throughout the project so far. In our first column, we have our biochar treatment, the no biochar apply control, 0B, the biochar equivalent to 2,000 kilograms per hectare, 2B, and the 4,000 kilogram per hectare rate, 4B. In the remaining 3 columns, we have our soil water pressures at depths of 15, 30, and 45 centimeters, again, measured in units of kilopascals. As we can see here, there are no significant differences of soil water pressure at the 15 centimeter depth. However, at the 30 centimeter depth, there is a significant difference in treatment 0B and 2B, having significantly lower soil water pressures than treatment 4B. At the 45 centimeter depth, treatment 2B is significantly lower than treatments 0B and 4B. To further analyze soil water pressure at all three locations, I took a look at the overall hydrograph for each of the three farms, and I identified a period of sustained high soil moisture immediately followed by a period of sustained low soil moisture. The purpose of this was to see if what the effect of biochar applications did on retaining soil moisture during the sustained period of low soil moisture following that period of high soil moisture. In this chart on our y-axis, we have our soil water pressure measured in kilopascals. And the x-axis is our date ranges. I measured for Dumas a period of sustained high soil moisture from June 3rd, 2024 to June 9th, 2024. The sustained period of low soil moisture I determined to be from June 17th, 2024 to June 27th, 2024. As you can see in this chart, biochar treatment 4B throughout the whole low soil moisture period is significantly holding more soil moisture than treatments 2B and 0B. This table displays Newport soil water pressure by biochar treatment, again for all sampling dates of the project. This table is similar to the one we saw for Dumas with our biochar treatments and soil water pressures at all three depths. There are no significant differences in soil water pressure throughout the project at Newport for the 15-centimeter depth. However, at the 30-centimeter and 45-centimeter depths, both biochar treatments are significantly lower in soil water pressure than the no applied biochar control. Similar to Dumas, I looked at the Newport hydrograph and did the same thing. I isolated a period of high sustained soil moisture followed by a period of low soil moisture. The high soil moisture period I determined to be from January 4th, 2024 to January 9th, 2024. And the period of sustained low soil moisture was determined to be from June 6, 2024 to June 21st, 2024. Again, on our y-axis are soil water pressure measured in kilopascals, and the x-axis are our date ranges. As you can see here, in the period of low soil moisture, biochar treatment 4B is significantly holding more soil water during this low soil moisture period than treatments 2B and 0B. This table displays Stuttgart soil water pressure by biochar treatment for all sampling dates of the project. Similar to the first two tables of this type, biochar treatments and soil water pressure at all three depths. We see at Stuttgart, biochar treatment 4B is significantly lower in soil water pressure than biochar treatment 0B, the control. When I did the same thing with Stuttgart as I did with Dumas and Newport, we found that in the low soil moisture period, biochar treatments 2B and 4B were significantly holding more soil water throughout most of the duration of this low soil moisture period than 0B, the no applied biochar control. This table may look a bit jumbled, but it's actually, when I explain it, it may become a bit more clear. This is soil nutrient status and CEC results from 2023 to 2025 for Dumas. I analyzed these by year. In 2020-23, I took soil samples from each plot designated to receive biochar additions from either the 2B treatment, 2,000 kilograms per hectare, or the 4B treatment, 4,000 kilograms per hectare. The soil samples collected in 2023 were collected right before the first biochar application to these plots. In 2024, I collected soil samples again. This was 1 year after the first biochar application. After the 2024 soil sampling, I collected soil samples again, and this is reflected in the 2025 soil sampling event. So I'm analyzing these biochar treatments by year. As we can see here, biochar treatment 2B at Dumas, we see increases in soil test phosphorus, soil test potassium, soil test calcium, and for biochar treatment 2B. For treatment 4B, we see the same trend in soil test phosphorus, in soil test potassium, and soil test calcium. Similar to Dumas, this table for Newport is in the same vein. For biochar treatment 2B, we didn't see any increases in soil test phosphorus or potassium. However, for biochar treatment 4B for Newport, we saw increases in soil test phosphorus and soil test potassium from 2023 to 2025. For Stuttgart, for biochar treatment 2B, we saw significant increases in phosphorus and potassium, along with calcium and magnesium. For biochar treatment 4B, we did not see any significant increases in soil test phosphorus, soil test potassium, or soil test calcium from 2023 to 2025. This table displays bulk density by biochar treatment at all three locations for 2024 and 2025 combined. I took bulk density samples in 2024, and I took them again this year in 2025. For the purposes of this presentation, I analyzed all bulk density for both years by biochar treatment. So these numbers are the averages of both, pretty much the averages of both years. As we can see for our biochar treatments 0B, 2B, and 4B for Dumas, Newport, and Stuttgart, there were no significant differences in bulk density. However, there is a trend as both biochar treatments are numerically lower than the no-apply biochar control in both years, or average for both years. Observations and takeaways to date in this biochar project so far. We noticed that significant differences were observed among biochar treatments and soil water pressure for all sampling dates. At Dumas, we noticed a significant difference in soil water pressure for treatment 2B at the 45 centimeter depth. At Newport, we noticed biochar treatments were significantly lower in soil water pressure than the control at 30 and 45 centimeters. And at Stuttgart, we noticed that biochar treatment 4B had significantly lower soil water pressures at all sampling dates compared to the no biochar apply control. And when further analysis of soil water pressure, identifying periods of high soil moisture and low soil moisture, we observed significant low soil moisture period. Specifically, biochar, the 4B treatment was significantly holding more soil water pressure during this low soil moisture period than the no biochar apply control. We also observed significant differences at all locations in soil nutrient status in CEC for biochar treatments 2B and 4B relative to the no biochar apply control. And finally, we observed that there were no significant differences in bulk density. However, both biochar treatments were significantly lower, not significantly, numerically lower in bulk density than the control at all three locations. We noticed that significant differences among biochar treatments may be the effect of how these farms irrigate. At Dumas and Stuttgart, they use furrow irrigation throughout the growing season, whereas Newport just relies on rainfall. There is no irrigation whatsoever at this research farm, or at these plots on this research farm. Also, we observed that significant differences between biochar treatments can illustrate how soil texture may have an effect on soil water pressure. This Dumas site is characterized as a lighter silt loam, and the Newport and Stuttgart soils are more heavier silt loams, as evidenced by those bulk density samples. Ongoing and future efforts in this biochar project, we will be collecting additional soil water pressure data throughout the calendar year 2025. This will produce 3 years of soil water pressure data, and I would continue to use statistical analysis to determine significant differences between biochar treatments for soil water pressure data. Also, we will be conducting ongoing maintenance of soil water pressure probes and associated data loggers. Additional soil health data will be collected in the spring of 2025. This will produce 3 years of soil test data. And we are also analyzing for percent nitrogen and percent carbon, as well as organic matter. I didn't include these in this presentation because I haven't received the results back from the Fayetteville lab just yet. And we also will be evaluating the effect that individual biochar treatments have on soil nutrient status, pH, CEC, and organic matter from collected stratified soil samples at Dumas. I went to Dumas and collected stratified soil samples at 0 to 2 inches, 2 to 4 inches, and 4 to 6 inches to see if we had any effect of biochar on these stratified soil samples. I haven't received the results yet, and when I do, I will analyze this statistics, and we'll try to get that available to whoever is interested. Also, I will continue to prepare and submit written materials about this biochar project. This consists of quarterly reports to the NRCS, also compiling data and text for possible publication in a peer-reviewed scientific journal. I would like to acknowledge my team members that have greatly assisted me on this project. My supervisor, who probably many of you know, Dr. Mike Daniels, my co-workers in this project, Lee Riley, Brett Cooper, the plant in Monticello, Arkansas that supplied this biochar, EnviroPack, and the Arkansas Discovery Farmers, Wes Kirkpatrick and Terry and Trent Dabbs, and the county extension agent in Newport who works at that research, who used to work at that research station, Matthew Davis. And with that, I'll be happy to answer any questions you may have.
Thanks, James. Really appreciate that presentation. Just a question from me. I know you mentioned a biochar production facility. So in terms of production, at least here in Wisconsin, we just don't seem to have access to like a large enough quantity of biochar to make it economically feasible, or at least like not that we've seen it at the moment. What is production like there? Like, are farmers getting what they want at a price that works for them?
It's still in its infancy. For a while, that Monticello plant was the only plant in Arkansas that was producing biochar. It's advantageous because it's in Southeast Arkansas. It could be transported to these row crop farmers with a minimal amount of trouble. Since then, there have been 2 plants that have opened up that I know of in Northwest Arkansas. So evidently the biochar production is becoming more widespread in Arkansas. As for the farmers having trouble getting this biochar to their farms, I don't know the answer to that yet. Hopefully the results that we produce in this project will encourage them to figure out ways to get biochar to their farms.
And one question that came in was the biochar inoculated prior to incorporation?
No, it was not.
Okay. All right. And then I think there was one more question. This one came in the chat and not in the Q&A, but what was the thickness of biochar challenges? What are the challenges and life cycle for single use?
You mean thickness as in texture?
Uh,
I would imagine that. Okay.
Perhaps I would take it however makes the most sense.
Well, this biochar, I contacted before I went down there and got the biochar. I contacted the plant manager. I said, just give me the biochar you recommend for agricultural use in Arkansas. The product he gave me, the texture ranged from fine dust particles to particles as big as one's thumbnail. It was very wide ranging. Let's see.
And then the other part was about the challenges and life cycle for single use.
That's a good question. It's kind of hard to answer right now because we've been applying it every year, and there's in the literature I've read, people just apply or people apply just at one time and manage or evaluate the effects after that. I guess it would be up to the farmer on what they want, whether they want to fertilize the soil or try to fertilize the crop.
Yeah, those are like, it's a complicated assessment, right?
Right. Biochar is not a one cure-all. There's still a lot of unknowns to it, and we're experiencing that down here.
Yeah. Well, thank you. We appreciate you sharing that and looking forward to what the future pieces say for that. So it looks like we have a few minutes left. So maybe what we'll do is go back to a couple of the questions that were in the chat. I think there was one for Vermont that was just asking about what pieces are the residential community doing research on for their input for conditions to the lake that you mentioned. Just kind of like a question about that balance between the agricultural sources and other sources and how they're all handling that together.
Yeah, I answered that one, so I'll make sure I say the same thing. Yeah, it is true. There is a lot of other businesses and residential areas throughout Vermont And I will say that in this particular area of the Lake Champlain watershed, it is a heavy agricultural area. It is one of the most polluted watersheds in the state. So there's been a lot of effort there over the years. So it's in the Jewett Brook watershed in St. Albans Bay. And so there's been a lot of emphasis on lots, again, of industry and agriculture. And I would say in Vermont, agriculture, certainly is doing the biggest lift compared to other industries and certainly the residential areas. And maybe I'll leave it at that. There is a recognition that there are, that water quality issues do stem from lots of different places, but our primary focus is on agriculture. So that's why we talked about that most today. But there are many other efforts too.
Yes, it takes all the things, right?
Yep.
One other question that I think is for your group, Heather, is how are you collecting or treating the tiled field drained waters? So Joshua answered that based on like the protocols, but I'm wondering, are you all working on anything or like keeping on
end of
horizon
tile.
for like treating tile?
Joshua could probably answer that the best. There have certainly been some efforts and emphasis on that, but I'll let Joshua go. Yep.
Yeah, sorry if I misunderstood that question. Yeah, so we have tried, and probably many of you are aware of efforts in the Midwest. So we've tried some of the same type of filter structures here in Vermont. The most recent, it was with a zero valent iron shaving material mixed with pea gravel at the end of tile outlets, and we're really happy with those. Actually, we've seen upwards of 85% of soluble phosphorus removal over 2 years on one of those systems. So our largest concern, so looking good for soluble P, but we are concerned about potential clogging over time with sediment. We do see sediment in our subsurface tile flow. I saw the charts. I think that Tim presented not a lot of sediment there in those systems, but we do see sediment in our tile flow. So I think it's just an issue of tracking that and seeing how long these filters last before they'd have to be, kind of either flushed out or replaced or dealt with in some way.
Right, everything works for a certain time. I don't know if you misinterpreted that question. I just was curious because it's something that we're starting to get questions about in Wisconsin. There was a time where it seemed like sort of the tiled treatment practices were really only suitable for really flat conditions. And I think we're starting to see, at least in Wisconsin, more curiosity about those treatment practices. So mostly my curiosity. Okay, I'm going to take one more question from the chat for Ellen and Lindsay, or from the Q&A for Ellen and Lindsay. And then I think maybe what we'll do is put up the ending survey, and then we'll put up the QR code for CCA credits while they are answering that. So Ellen, you answered this in the chat in text, but I just wanted to kind of bring that out in conversation. So the question says, for the grassed waterway group, is there concern of phosphorus accumulation in the grassed waterway over time, or is the grassed waterway able to be harvested to mitigate this potential?
Yeah, that's a great question, and I'll answer the second part first. So if a grassed waterway is put in cooperation with NRCS to receiving cost share, they generally do not allow that area to be harvested or to be grazed, at least while it's under contract. So generally that's not allowed. But in terms of whether or not it's a concern that phosphorus might be accumulating in that waterway, as far as I'm aware, I haven't seen any studies suggesting that the soils in the waterway or its vegetation would be a significant source of phosphorus losses to the edge of the field. More of the concern would be if over time we're seeing a lot of sediment accumulated in the waterway from infield losses. And in that case, the shape of the waterway would change over time to the point that it wouldn't function as designed. And that's where you'd need to have some renovations in place to get it back to the design standard. So another reason why those waterways work really well with some in-field management to reduce the sediment load and just extend the lifespan of that waterway before it needs work.
Thank you. That's fabulous. Yeah, really layering those practices together, right? That's how we get the best use of all of them. So thank you to all of our panelists. You see the poll. If you haven't answered it yet, we would really appreciate if you would. It's really helpful information for us. We want to keep improving your experience and making the most of your time that you choose to spend with us on something like this. So we appreciate you answering that. So with that, if you're looking for CCA credits, the QR code is on the screen. If you have trouble with that or can't make it work, please just put your CCA number in the chat box and we'll make sure to get those credits submitted for you. So with that, I want to say one last thank you to our presenters and to our partners that have spent the time with us today. Appreciate you asking good questions. We want to invite you to visit each state's website, and also the recordings for today will be uploaded to the Minnesota Ag Water Resources Center YouTube page within a couple of days. So if you have any questions in the meantime, feel free to get in touch with any of us that were here today. But again, thank you so much. Have a wonderful day here in Wisconsin. It's sunny, so enjoy spring.